Okay, this is a diary update basically. What am I saying? So this is my diary update. So I'm trying. Today's date is the 4th of March. The time now is 5:01 p.m. So basically, today I've got my diary here. So, so this is basically for the drift system, but it's simply a model for a holographic system. So it's a holographic interface I'm building for Mmuko OS. So basically, you get drift is a tripartite auxiliary vector in R3 in a set of real R sub 3, XYZ, such that G is a graph, G equals A, V, so this thing. You look at it here, 1 second. So uh, you have, drift is a tripartite auxiliary vector in R, in semi-set in R, such that G, V, and W is a weight. So G is a graph equals a tuple A, which is an edge, V is a vertex, and W is a weight. So basically, the weight of a graph is very essential. Understand? So go here. So in three colorable red here, basically in a bipartite colorable system. But it says here basically red. So you get red, red. So you get here three colorable, three colorable red, red shift. Green is for green shift, and yellow is for yellow shift. But you get yellow and orange. So you get four states can be. So these are states. So you get red and orange. Because I'm changing it now. Red, orange, yellow, orange, and green orange. That's basically so that's what I'm saying. So you get a drift is a tripartite auxiliary vector in R3 such that G equals E, V and W, where G is graph equal to the edges, the vertices, and the weight. Now the weight is determines a snap. So the weight is the weight of density of a graph, which is known as graph density. So it takes into account the in-memory processing of system. So imagine if you take a model of three people facing each other. And one person is moving away. I can just draw it up. So you're gonna have the graph equals to is a graph. G is an edge, V is a vertex, and W is a weighted graph. It's a weight. Is the weight of the graph, or W is weighted of the graph, and weight on a graph, which can give you the density property, which is like a system of how much have mean, mode, median, average, basically. Where C is the computational cost of the graph. So where C is the computational cost of a lattice transversal. That just means there's a multi C of the cost of on the lattice transversal via best system. I'm trying to model this properly because it's gonna be for my Holo interface for my website. So basically, you're gonna have graph G, E, and V have a weight of W, and basically the edge has a weight of W, and the edge has the weight. So the gradient has the weight. So basically, the weight is the cost of a function. So can be basically it takes into the two bipartite cost, and that is the cost of an edge transversal and the weight of a node. So you have the weight of density. So you're gonna have the weight of a node. So you're gonna have the weight. So for example, you're gonna have bipartite nodes. So you're gonna have two bipartite colors. You're gonna have red, orange, yellow, orange, and green, orange. So basically, if something is moving away from, if something is static, it's orange color. But if it's shifting away from you, it's red color. So if it's like if I'm looking at someone and someone's moving away from me, it's red color. And basically, that means that the edge is drifting, and orange indicates that it's static. So it's like it's one place. Yellow is moving orthogonal away from you. So it's drifting away from you, but it's like a 90 degrees angle. So it's moving 90 degrees away from you. So yellow is drifting, red is shifting, because it's just moving away from me. But the red is also drifting. So red, orange, and green. So green means it's close. So if yellow means it's coming closer towards or moving away from me, green means it's moving closer. So green means it's moving closer. Yellow means it's moving outward. So at right angle degrees, which is very important because this is you get three colors. So I'm facing one another. So it goes to define a UI interface that works the system mathematically. So mathematically, this will be defined as, and I know this one, but this is bipartisan coloring, and they are trident position. So this is the lattice. So I was trying to do yesterday. So this is my lattice. So basically, this is use for ahead of time computation over system. Because if you know somewhere, you can see somewhere else. Basically, you can estimate the cost of going somewhere else, and that's the if the weight is too much or the distance is too much of the node, it will not be able to see me. So it doesn't want us to you have to estimate. It's not estimation. It's not it's just like it's a triangular bearing system that results in this kind of system of via lattice property. So you're computing on lattice basically lattice meet, lattice join, lattice disjoint, and lattice join, lattice meet, all the way to stand lattice. So that's the drift. So the drift is defined as the system. So if I'm facing, so if I'm facing a camera and I'm moving away from the camera is moving away. I'm moving away from the camera. The edge should glow red. If I stand still and facing the camera, or the camera is watching me, I should be orange. If I start walking 90 degrees away from the camera is now in yellow mode. Now, if I start moving closer to the camera, it will show me green. But because we change based on the camera's perspective of me, that's what you go. So you get two formulas here. You get a spline interpretation. I'm busy. A spline as such given a spline s given 1 minus t times c times t times p, where w is the weight of the average. So you get the weight of the averaging, which is basically the spline between start points, basically between camera point. So the camera is there, but it's looking at me. So the camera is there, so it's looking at me, but it's facing waiting. But you get so you get if it's 1 minus c, usually in the I'll draw it from this 1 minus c times t times p, but this will be two thirds c times 1/3 two thirds c plus 1/3 t plus p. You know, 1/3. The weighted average is important. 1/3. So this is two thirds two-thirds c plus 1/3 t times p. And this I'm saying is this is the weighted average of a system of non-related question. This algebra is saying that it's two-thirds of the graph that we saw. So this might not do verification. You have to verify the system maths. So this is basically saying in algebraic form the disjoint or the meet, the disjoint, the disjoint or non-union is distributed over 1 minus t times c times p times t times c, which is where 1 minus t times c is the camera point, t is the time interval, and p is the projected point. Is the point that's projected over weight of system. So point one, point x, point s equals one and so and you get a start equals to x1 minus x1 and y1, n equals to x2 and y2, and midpoint equals to time plus n divided by 2. Now divided by 2 will give you the midpoint over the system, and that will start you computing the weight. So so it doesn't matter where it is, you get it's like you get a piecewise function that gives you algebraic form and integral form. So the goal is to have the system compute something ahead of time, but it gives you some kind of so you can have a smooth UI interface. Smooth UI, I'll use it for something else, but this is smooth UI. So you get the inverse kinematics smooth UI because it's loaded ahead of time and it knows what's going to come up next in the UI interface. So it's basically not a basically you gotta have the egg model too, and the egg model basically can give like so called a goal because if you have a parachute drop and you get an inverse kinematic model. So if you draw some kind of payload onto something, you got like an egg falling into someone's hand, you're gonna slow down and so people can catch it. So the egg gonna fall into the hand. Because basically the same parachute experiment I'm saying, but the parachute system you have an egg and the egg is gonna fall down, you're gonna have some mechanics that need to fall down slowly when it reaches a certain altitude. basically. It's called inverse kinematic because you are thinking about the user ahead of time, the wind resistance as it comes down. As it comes as the player is developed. So you're gonna put the x. So if x mod of two equals even, x equals odd. So if x mod of two equals to, so these are two properties. So you get joint properties. So these are additional properties. So the classifier says if x equal mod of two equals zero, and x if x mod of two is even, then x equals even. Because equals to zero is even. So you classify as one set and you classify as one set. So x is odd. So the goal is to have property separated in distributed in union, so they are computable over the lattice. And lattice will give you the properties, and that property is b squared minus 4ac, which is the increment of the system. That will give you um, property distributed across sets where you have a property P, a property P, given a weight and equal to geometric weight, geometric and algebraic solutions to the space. B squared minus 4ac, which is a change in the piecewise function or context switch between the piecewise functions. Thank you guys for watching this video. But that's how the system works. So it's a holographic system, but it's a website. So it doesn't matter whether you have an image or not. You can use it. Endlink goes to have the linker link the images, and the images will be or in single linker will link the images into a binary that's loadable by any foreign function interface, such as Python, via an index or HTML file. That should put something. So the goal is to have an index and HTML file with a single Go application to link all the images into a video codec system, and they will pay frame by frame, and someone to be interactive with image with seamless interactive system. This is where you put your finger or not on the screen, or you move your mouse. The system is a fluid system. It's a fluid holographic system. Thank you, Munadi, for watching the video.